Good evening, everybody, and welcome to BrisScience. Thank you all so much for coming out tonight. I am your MC for the evening, Joel Gilmore, and if this is your first time, welcome. This is BrisScience, a lecture series presented by the University of Queensland, where we aim to bring scientists who are not just brilliant researchers, but also amazing communicators to share their work and their passion with the audiences of Brisbane. I would like to start by acknowledging the traditional owners of the lands on which we're meeting tonight, both here and for people watching at home on YouTube, wherever you might be, and pay my respects on behalf of BrisScience to elders past and present. And we acknowledge that our actions here always have an impact on the land and the waters where we live and work. We try and minimise that and walk carefully wherever we can. So we're going to introduce our speaker in a moment. A little bit of housekeeping first of all. We're going to have a presentation first, followed by some Q&A, and we're going to take those questions through our website. So there is a QR code. Great timing, tech team, I love it. There's a QR code there that you can scan, and you can put your questions in at any point. We'll put it up again after the talk as well, so don't stress if you don't grab it now. But also a great opportunity to put your phone on silent and to make sure that you don't need to phone a friend during our talk. Afterwards, we will be having some food and drink from St. Leo's Catering outside. We'd love for you to join us out there. We're, of course, at the wonderful Edge, our wonderful venue partner here. So please hang around, have a bite to eat, and talk about everything you've heard tonight. All right, without further ado, our speaker this evening is Professor Jack Clegg, who is a Professor of Inorganic Chemistry at the University of Queensland. He has got a wonderfully diverse background. He studied history, German, a Bachelor of Laws, and of course, chemistry, leading to his talk tonight, talking about the work he and his team have been doing, developing the world's most flexible crystals that will, instead of shattering, can be bent and twisted. So he has won multiple awards for his work, including a Prime Minister's Science Prize. So you know that tonight's talk will be, of course, crystal clear. Thank you. Please put your hands together and welcome the amazing Professor Jack Clegg.
Thank you much, Joel. Thank you very much for you all coming as well, and thank you for tuning in to watch online. Crystals are remarkable things. They're all around us. We interact with them all the time, but they're fundamental to all sorts of technologies, things that you probably didn't realize had crystals in them. Internal combustion engines, watches, lasers, and mobile phones, computers. All of these things rely on crystals. And so I'm going to tell you now a little bit about some of the things that we've been doing to see how we can change the way that we think about crystals, because these are things that we know and love. What I'm going to start with is a little bit of an introduction about some concepts that might not be readily accessible, and we'll give little bits of them for you in different ways so that hopefully I can talk about some of the finer detail without leaving everybody behind. So the first thing I want to talk about before we get into the how, what, and why of flexibility in crystals is just to start by thinking about what a crystal is in the first place. Now, a crystal is simply, and I say simply, but there's a lot of things that go on here, a three-dimensional pattern of molecules, of ions, or of atoms that are arranged infinitely in space. And when I say infinitely, well, I suppose we could have one as big as the world if we really wanted to, but really we're talking about small little crystals, but with an essentially infinite number of atoms or molecules in them. We're talking about lots of things, but every single one of those items in the crystal is precisely arranged, so that they are arranged exactly the same way in a periodic fashion. And this regular arrangement of molecules, or of ions, or of atoms, is what gives them the really fundamental properties that we can use, that can underpin all of these technologies. When they're really, really excellent crystals, we call them single crystals, meaning that there are very few defects in those crystals. So these sorts of properties that end up are electrical properties, optical properties, and these are very useful, as I mentioned, in all sorts of different things. But I suppose what we've all understand about crystals ourselves in the way that we interact with them on the everyday scale is they're not really very flexible. In fact, when we think about a crystal, in general, we think that if we attempt to do something to them, we apply some stress or strain to them, that inevitably they're going to irreversibly deform. They're going to crack or break. And so this poor calcite crystal here is demonstrating that aptly for us. But if you look carefully at this calcite crystal, you'll see that it's breaking in very defined ways. It's forming very clear cleavage planes. And the reason for it forming those planes, forming those particular shapes, is because of the arrangement of the atoms and molecules in three-dimensional space inside that crystal. Turns out calcite is a two-dimensional mineral. That is, its structure forms two-dimensional sheets which repeat infinitely over and over throughout the crystal, and when you hit them, those sheets stay together and they break apart in these cleavage planes. So we can relate the fundamental arrangement of atoms on a very small scale to the way that they macroscopically respond. Now, apart from a polymeric crystal, a mineral like calcite, the same sort of things happen if you make a crystal of molecules. And this is just a very simple inorganic molecule called ruthenium trisbipyridine. It's a very famous molecule, it doesn't mean a lot to you, but here's the lovely crystal of it, and you'll see when we just apply a tiny bit of force to it, it again shatters and it breaks. That's exactly what you would expect. That's consistent with our everyday experience. And it's probably not going to be any real surprise to you that if you attempt to bend a crystal of the same material, it's also not going to respond very favorably to that. It's going to just break, to deform irreversibly. So we need to think about a little bit how we can then change the three-dimensional arrangement of atoms if we want to get things to have a different property of crystallinity. So, next concept after a crystal. Again, something that we should all know and love. Humans have been using it for millennia. Elasticity. Okay? So we can just take any little bit of elastic that we know of and we can bend it or we can stretch it and it will go back to the shape it started with. Okay? Robert Hooke, about 300 years ago, worked out that there's a proportional relationship between the force and the distance that you can stretch a rubber band or a piece of elastic. Anything that's elastic, right? And that we apply a force, and the further we put it in, the more force we have to put in to stretch it. What happens though if we stretch something too far, of course, is that it's going to break. It's going to deform elastically, or inelastically, right? It's hard with a rubber band. We run out of space, but it's easy, as we've seen with a crystal. But when we run past this elastic point, where we no longer have a reversible response, we call this the elastic limit, okay? And things break or deform in an irreversible way after that. They no longer return to their original shape. So we can talk about stretching, or we can also talk about bending. The same thing applies. You can bend something elastically. A couple of little things that I just want to highlight here, just for later on in the talk. If you take a crystal or any beam of a certain length and you bend it elastically, a couple of interesting things happen. The inside arc of that crystal gets shorter, the outside arc gets longer, and the length in the middle doesn't change. If you bend something irreversibly, something in a plastic sense, the inside and the outside don't change length. They change the same, or they stay the same, and instead we get slippage between different planes. So the things we need to look at, if we're looking at a change in a crystal, if we want to determine if something's elastic or not, first we're looking at reversibility versus irreversibility. That's an important one. And secondly, we're looking at some of these basic changes in size and shape. Third concept, and hopefully the last one, chemical bonds and intermolecular interactions. Elasticity is important. It's not just the way we interact with things. We can actually think about the chemical bond between atoms in a molecule like an elastic band, like a spring. They respond elastically. They reverse, they vibrate around. But every different bond within an atom or a molecule has a different spring constant. It has a different strength. So just looking here at a molecule of acetone, what the atoms are don't matter, but the point is we can look at the different bonding types here. Here between a carbon and an oxygen has a strength of about 749 kilojoules per mole. A covalent bond here between a carbon and a hydrogen is about 411 kilojoules per mole, or a covalent single bond between two carbons here is the weakest one, 346. So what is a kilojoule? Again, we have to remember that a joule, so 1,000th of a kilojoule, is just the amount of energy it takes to lift 1 kilogram 1 meter. Okay, so kilojoules, quite a lot of energy compared to just the things that we move around. But bonds in chemistry or between chemicals aren't just within the molecule. There are also weaker sets of bonds that extend between molecules. These are described as intermolecular interactions or supramolecular forces. So if we take two of these acetone molecules, for example, and they line up like this, like they would in a crystal, there's a stabilizing interaction between them. This is a much weaker interaction, only about 10 kilojoules per mole compared to the hundreds of kilojoules per mole that we were talking about for a bond. It's going to be really easy to move two molecules apart. It's going to be much harder to break the atoms or the bonds in the molecule itself. So the types of intermolecular interactions, just to highlight them, are really weak dispersion forces. These are things that we, for example, have in the air that we breathe that keep the molecules from flying off into space. Dipolar forces that are a little bit stronger. Hydrogen bonding, which means that water is a liquid. Pi stacking, which is just probably important for this, but is an arrangement of aromatic molecules between one another, or the strongest, halogen bonding, up to about 25 to 200 kilojoules per mole. So, we've got some insight now. We want to then move on and think a little bit about our elastically flexible crystals. First, I suppose I've already said, we're going to want to try and find something that's elastically flexible because we might be able to combine the properties of a crystal, that is all these really useful properties, with something, or the properties that we don't normally expect crystals to have. Properties like elasticity. This means that we might be able to make a telephone that we could roll up and stick in our pocket. Or we could use crystals in places where they wouldn't break. So we like to say that ideally, in these flexible crystals, we want to combine the properties of soft matter, that's things like plastics, with the property of hard materials, like crystals. So, how did we go about doing this? Well, thinking about science, we always start with an observation. So this was our first observation of elastically flexible crystals. This looks horribly complicated. You can make it in about 15 minutes in the lab if you really try. It's called copper bromoacetyl acetonate. And it doesn't really matter what the chemical structure is here, other than we have an organic component with the carbons, oxygens, and bromine, and we have a metal, a copper component. And when we make this material and we grow it into crystals, they form long, thin needles. So these crystals here, or this one in this photo, is about a centimetre long. And when you take a crystal, and one of the properties of crystals is that you can fire X-rays at it and get a lovely diffraction pattern, which allows you to work out where the molecules are in three-dimensional space. You also have to mount them in such a way that you play with them under a microscope. And so we were playing with these crystals under a microscope to get an X-ray diffraction pattern from them, and we noticed when you applied a little bit of force to this crystal, you could bend it. And that seemed very strange. So here we take our crystal, we apply a bit of force, it bends nicely, and we remove the force, and it springs straight back. So it's elastically flexible. Now, of course, everything is a little bit elastically flexible, but to observe this in a crystal was odd. So we decided to move on from there and to start thinking about what there was about this crystal structure that allowed for these crystals to be flexible. So from our X-ray diffraction pattern, we can get information out about that X-ray, about that crystal structure. So first, again, just demonstrating how flexible these crystals are. Here's a much longer crystal, about 5 centimeters long, and you can see that you can bend it all the way around into a loop. What we did then was take one of these crystals tied in a loop, and we fired X-ray diffraction, an X-ray beam at it. And this is what we see. We see a very broad diffraction pattern. So this is quite different to the nice, sharp, clean diffraction pattern that we were seeing here. Okay? It's very sharp, all of these spots are well resolved, but when we bend the crystal, we see now that the spots are still there, but they're much broader in shape. And that tells us straight away that we don't have this uniform arrangement of atoms and molecules in the crystal anymore. Something has happened on the molecular level to allow these crystals to reorganize. If you break the crystal again, it returns to the original diffraction pattern. They go sharp again. We're seeing elasticity in our diffraction pattern as well. So this is the crystal structure itself. When we think about a crystal structure, we think about 6 different parameters which describe its unit cell. We think about the length of 3 axes and the angles between them. We also have a symmetry relationship. So when we look at this crystal structure, we see these atoms, or these molecules here, they're nice and planar, and they line up along the b-axis. These arrows here represent a pi-pi interaction, so quite a strong interaction that is holding them together. And perpendicular to that interaction is a weak halogen bond. So we've got quite strong interactions between these molecules running up the crystal, holding them together, and very weak interactions orthogonal to that. So the question is, how far can we extend this? Is this a unique property to just one crystal, or can we make many more examples of crystals that have this same property? What sort of crystals will have elastic flexibility? So to start with this, we're going to start with a hypothesis, just based on our first observation. We're going to think that maybe a combination of complementary intermolecular interactions with different strengths, which are arranged approximately orthogonally, might lead to elastic flexibility. So again, we had this nice planar molecule which had our pi stacking, and about 90 degrees to that we had halogen bonding. So because we're good scientists, we went about testing this in the only way that we really know how, which is to make lots of examples. So this is a readily accessible molecule if you're a synthetic chemist like I am, and so we can make lots of different variations in all of these different positions. We can have access to more than 100 different metals in the periodic table, for example. We can change these almost infinitely. And so these are the sorts of things that we went and made. So more than 100 examples now of very closely related molecules to work out how and why making individual changes will affect the elastic flexibility. Once we make these molecules, we grow them into crystals, and then we start to try to test them. And we don't test them in any particularly hard way. We simply try and do what's called a 3-point bending test on them. We just see if we can bend the crystal and if it straightens back out again afterwards. So here's a lovely example of, again, the same molecule or a very similar molecule, but where we've changed the metal from copper to palladium. And again, we can see that we still are getting elastic flexibility in that crystal. The best one that we've found so far was actually the second crystal that we tried. And it's the simplest one. Actually, it's copper acac. And it's made extensively in undergraduate labs to teach people how to make these sorts of chemicals. And so here's a nice long crystal of copper acac, about 5 centimeters long. And here's Anna trying to see how far she can bend it. So you can tell it's frustrating as well as interesting. But eventually she managed to tie one in a knot. So that's how flexible this really can be. So this, again, this crystal is about 5 centimeters long. It's about as thin as a piece of fishing line, and you really can tie it in a knot. And if you look closely up here, you'll see that that also means it needs to twist, right, to get it to pass over one side from another. I'll zoom in over here. They're intensely beautiful and very flexible things. But again, we wanted to work out what it was about this crystal that made it even more flexible, and to see what changed when we were bending it. So before we did that, we thought we'd do some other testing. We'd compare all these crystals to other molecules, for example, to polymers that we know and use to make plastic bags and everything else. So the first thing we did that was talk to some engineers about what sort of testing they do on plastics. And the first thing they said was, well, if you make something elastic, you need to see if you can stretch it. And so we grew, again, some really large crystals of these materials, and we stuck them between these things, and we did some tensile testing experiments. And when you do that, you apply force equally between you monitor how far this crystal extends. And it turns out you can stretch a crystal of about 5 centimeters, about 0.1 millimeters, which is nearly 5% of its length. So that's quite a way. But also when you're doing this, you can measure how much force you're applying. And that will also tell you about the elasticity that you're experiencing. So you recall when I said something that is elastic has a linear relationship to how far you can stretch it. So when you measure these things, you can get linear plots out, which demonstrates elasticity is present. So here are 3 different crystals, and we've just measured them in our tensile testing machine, and you'll see they're all nice and linear until you break them at some point, and they catastrophically fail. What you get from the slope of these curves is an elastic modulus and a fracture strength. And so what we see here is that the fracture strength is almost the same as polyethylene, so the material that's in plastic bags. So very interesting. You can't just stretch these things. Of course, we've seen we can bend them, but how far can we bend them? And to do that, again, our engineers have wonderful things called a 3-point bending test. So we take our crystal and we apply a force and we measure how far that force goes down. And so what we've done here is just taken one of these crystals, we've applied a bend, and then we've removed the force and done it over and over again to show that it's elastic. Not only is it a straight line, but it is also reversible. And you can keep on bending it until you reach a point a bit over 1% strain where we start to see irreversible deformation, and it plastically deforms and it ends up looking like this. So there is an elastic limit at about 1% strain. The elastic modulus that we get out of this from 9 crystals ranges between 2 and 8 GPa, and that's about the same as nylon. So these crystals are behaving just like soft materials. So the question we wanted to ask next was, how is it that these crystals are behaving in this way when we know that all crystals aren't elastic? What is it about these crystals in particular that allows us to answer, to bend them in this way? So again, let's think about the crystal structure. Now, again, I told you that in a crystal structure there are 6 parameters, and I want to just highlight a couple of things for you here. So here is a picture of a crystal of copper acac with some molecules within it. When we look at the crystal structure, we again see that there's a stack of these molecules with a pi-pi interaction between them that run up the length of the crystal, all the way up the length of the crystal. But when we look down the length of the crystal, there's only very, very weak van der Waals interactions between those crystals. So this is good because it's consistent with our hypothesis. We want strong interactions in one direction, and roughly orthogonal to that, we wanted much weaker interactions. So we're starting to build up some more information here. But I want to also just point out that the important thing to think about here is that the B-axis of the crystal, this number here, 4.678, runs up the length of the crystal, and the A and C axes are orthogonal to that. The beta angle here is just this angle here, and we'll talk a little bit more about that in a moment. So we took some of these crystals down to the Australian synchrotron, where they have some wonderful facilities. It's part of our national landmark research infrastructure. It's a large particle accelerator that makes very, very intense X-ray beams, but it also means that we can change the size of our X-ray beams very easily. So we took some of our very flexible crystals and we fixed them in a loop. And here is our crystal fixed in a loop. And we used a comparatively large synchrotron X-ray beam, 100 microns, okay? So 1/10 of a millimeter in diameter, and we fired some of those X-rays at our crystal. In the straight part of the crystal here, where it's not really bent, the crystal isn't under any strain, the diffraction pattern is beautifully sharp. But where it's bent, the diffraction pattern is now again very broad. So we're seeing a change in the crystal structure, a change in our diffraction pattern from applying our strain to the crystal. We then went to another beamline, also at the Australian synchrotron, where they can focus the beam in a much smaller way. They can focus the beam down to 7.5 microns, so 7.5% of the diameter of the one that we just looked at. And so again, here is our crystal, and this little dot in the center of this axis is probably about the same size as my laser pointer, I suppose, is the size of the X-ray beam. And what we're doing is moving the crystal through the X-ray beam, and we're measuring the diffraction pattern as it comes through. We start on both sides, on the side of the crystal where there's no diffraction, and we move all the way through. And you'll see straight away with that smaller beam, even though this is in the bent part of the crystal, that those diffraction patterns are really sharp. And that means we're still seeing localized order in a very small sense that we don't see in when we use a large X-ray beam. The nice part about this is it allows us to work out what's happening at each position within the crystal. And so we can determine the crystal structure throughout, or how the crystal structure changes throughout the bent region of the crystal. So here's just some of that data. And what we can see here, as we move from the outside of the crystal to the inside of the crystal, remembering that the B-axis runs up the length of the crystal, we see that the crystal gets shorter on the inside and longer on the outside. And this is exactly what we expect from our theory of elasticity. Right? When we bend a beam, we expect contraction on the inside and expansion on the outside. So this is great. We're still in the elastic region of the crystal. We also see some other less expected changes. We see increases in the A and the C axes, which are the ones that are orthogonal to the B axis. And we see a decrease also in this B parameter. When we have this crystal structure then, data please excuse me, we can then plot this out in the size of the crystal itself, not just in the change in the unit cell axes, but we see exactly the same thing. So from the outside to the inside, we see the crystal going from long to short as we move from the outside to the inside of a bent crystal. We see an increase in the other direction, in the A and the C axes, but also quite interestingly, we see no real change in volume. And that's important from a physics perspective because it says we're not really doing much work when we're bending the crystal. We're putting energy in, but we're not really changing it to anything else. So what is the crystal structure, or how does the crystal structure itself change? Interestingly, there's no change in the distance that defines the pi-pi interaction. So our strongest interaction is staying the same. But what significantly changes is the angle between the molecule and the end of the crystal. So this means as we bend the crystal, the molecules change their orientation. Where on the inside of the crystal, where we're seeing compression, we see the molecules rotate to become more planar relative to the end of the crystal. And on the outside where they elongate, they rotate essentially in the opposite direction, getting longer. So just by rotating pairs of molecules, we can change the size and shape of the crystal. And whether that's us doing it or whether, I suppose it's the other way around, as we're bending the crystals, we're changing these molecules to change their orientation on the atomic scale. So we can do this with lots of our other crystals, and this is just to highlight that they're not all the same. Everything works differently. Here we've just changed a methyl group to an ethyl group, and here we've changed that ethyl group to a propyl group, and now you'll see that the changes in axes are all different. But again, the one thing that's consistent is these are bent elastically, and that we're getting the change nicely here in the B-axis, which in both of these cases runs up the length of the crystal from the outside to the inside. Again, instead of rotation in these, we actually start to just see the molecules drift further apart than another, rather than rotating. And this is because the intermolecular interactions are fundamentally different. But we're still getting changes to occur on the molecular level. Just to highlight how they're different, these are the same things but plotted out in 3 dimensions. So here was our first copper ACAC, where the B-axis was changing the most, and we had an elongation in the A-axis, whereas in these other two, we're getting very different effects just in the shapes of how they're working. So the next question is, why? Why do these things do that? Why is it something that we see in these crystals but we haven't seen in other crystals? And to do this, again, we had to change the way we were thinking about crystals from the first place. So we're going to go on and we're going to think about why. And the thing about why here is that where is the energy going when you bend a crystal? When we use an elastic band or a spring or something, we're putting in energy, right? We know that we can stretch this, and we know if we release it, we can change that energy from potential energy to kinetic energy, for example. But nobody knows, really, where the energy is stored in that elastic band. But this was going to be fundamental to us to understand why these crystals were behaving this way. So the question we asked ourselves was, could we work out where that energy is stored within a crystal? Could we work out where the restoring force originates? And this was interesting because when you look at the literature about what's known about all elastic materials, is that nobody really knows. We know that they're made up of springs, chemical bonds, so there's energy stored somewhere, but nobody knows precisely where. And this was the option we chose to investigate, or the challenge that we chose to investigate. So how are we going to do this? Well, first we're going to take a hypothesis. So we're lucky that because we're investigating odd things, we're investigating crystals that are flexible, we have an ordered system. And that means we might be able to pinpoint the intermolecular interactions because we have order. And so to do this, we decided to investigate the changes in the intermolecular interactions that occur in the crystal upon bending. Now this means we need to work out what the intermolecular interactions are doing on the outside of the crystal, in the middle of the crystal, and on the inside of the crystal. And so to do this, we had to do some pretty interesting things. So the first thing we need to do is to identify the potential interactions of interest. Now we can use computers to help us do this, but just by looking at the crystal structure, we've got a good idea. Right? We said that there was a strong pi-pi interaction in one direction and weak interactions in the opposite direction. But we can use the computer then to put some numbers on this. So we can verify that the pi-pi interaction, shown here in red, is much stronger than the weaker intermolecular interactions, the green one and the blue ones that are perpendicular to that. The numbers here don't matter, other than 80 is much bigger than 13 or than 10. The next thing we needed to do was create a lot more data. We only had about 20 data points from our mapping experiments, right? So not quite enough to model these things. So we need to do some extrapolation. But because we know the mechanism, we can use some linear algebra and some matrix calculations to do that. And so we generated about 200 different crystal structures, hypothetically, under various levels of deformation. So ranging from 0 to where we know the elastic limit of about 1% strain and even beyond. And then we calculated the energies of every single position of those. And we started to look then at what they meant. So this is the sort of graph that you get out. So what we're looking at here again is just each of those interactions. So the pi-pi interaction, that CH to pi interaction, the CH interaction, the red, the green, and the blue, and we can see that they're behaving and we can fit them very well, just like springs. We can also see, and this purple bar represents where the elastic limit is in the crystal. we can see that they're shifted all from their minima relative to that internal position. But if we sum them all up, they form a nice parabolic shape. And that matches very well to the minimum of the whole crystal calculation. Again, from these calculations, what we can get out that's quite interesting is not just our spring constants, but the consequence of that is by integrating under the curves, we can get out the energy that's stored in each particular interaction. So we can work out ideally what this means. So again, there's lots and lots of data points here, but the key thing to look at is comparing the slopes of the green and the blue compared to the red interactions. You'll see that the blue and the green slope down this way to the right, to your right, whereas the red slopes back the other way. That means on the inside of the crystal, the red interaction is storing more energy compared to the outside of the bent crystal, where the opposite is in fact occurring for the blue and green interactions. And so when you integrate all of these out, you work out that the pi-pi interactions weaken by not very much, 0.29 kilojoules per mole, while these ones here strengthen by 0.27. And the opposite roughly occurs on the inside. So this isn't a lot of energy when you look at this decimal places like this. But when you start to think about it in terms of how much energy that really is, things become significant. So it means that we're storing about 70 joules per mole on the inside and the outside of a bent crystal. Now again, 1 joule is enough energy to lift 1 kilogram 1 meter. So on the scale of a chemical bond, this is very, very little energy, but on the scale of which we interact with the world, this is lots and lots of energy. So that means if we took one of our bent crystals of copper acac, we could move a mass nearly 30 times its own weight, 1 meter against gravity. So that's a bit like an ant trying to lift up an elephant or something, right? It's a lot of energy for a little thing. So the next thing, and probably the most important, is we need to check that the results are physically reasonable. And to do that, we decided to have a lot of fun. And so to do that, we decided that we needed to try and make some cantilevers, and we should take our crystals, here's a nice crystal, stick ball bearings on them and see if they could spring back up against applying a force. And when you watch each of these ones, starting with just 12.5 times the weight of the crystal, just check if the crystal goes above the neutral position. And you should see that it does. And why is that important? Well, really it's important because that shows that we're doing work against gravity. So we're really springing back more energy in than we put in. So we go from 12 times the weight up to 30. Still elastically flexible. We can go up to 60 times the weight of the crystal. Probably getting to the edge, we're getting some deformation there, pushed it down too hard. But we can keep going on, we can go to 110 times the weight of the crystal. Again, thinking that this is getting close to our limit of 70 joules per mole, I guess, in some ways. Still elastically flexible if we don't push it in too far. Or we can just get silly. And we go to 150 times the weight of the crystal, and we'll see what happens. Just way too much force for it. So we clearly know where the limits of this are. So what do we know so far? Molecules in elastically flexible crystals, and this is probably every single crystal, we just haven't found the limits of where they are yet, reversibly reorganize in some way on the atomic scale to allow for compression and allow for expansion. So again, to get something that's elastically flexible, we fundamentally need to have that reorganization. We've located the origin of the restoring force in an elastically deformed material of any type for the first time. That is in the combination of intermolecular interactions. On the inside, it was stored mainly in the pi-pi interactions. On the outside, it was stored even in these weaker interactions. What are we doing next? Well, we're working towards ways of controlling the mechanical properties of crystals. And to do this, we're again changing the chemistry around the molecules to work out how we can reversibly tune the intermolecular interactions that are present, to find out the limits of this hypothesis that we need a combination of a strong interaction, essentially to hold the crystal together, and a weak interaction to allow movement. And ultimately, we're hopeful that this might allow us to use the useful properties of crystals in applications like flexible electronics, smart devices, aeronautics, and optoelectronics, where crystals have normally been just ignored for use because of our common perception that they're brittle and inelastic. And finally, I need to thank all of you for coming along and hearing me talk, but also thank the people who've worked on this with me. So first and foremost, a collaborator from QUT, John McMurtry, who's worked on this project for me for a long time. And then a whole host of other people, particularly Jack Evans, Ben Powell, and Mark Spackman, who assisted particularly with the aspects of calculations that are not my forte as a synthetic chemist. They're physicists and they're very good at what they do. But more importantly than them are the postdocs and students who've been working on this, whose hands you've seen bending these crystals up, who get into the lab more often than I do and work making these molecules and growing these crystals. And finally, we need to thank the Australian Research Council for funding this work, and particularly the Australian Synchrotron for having wonderful facilities that are unique in Australia and that we can use to do this wonderful science. Thank you very much.
Amazing. All right, we'll give you a moment to catch your breath. We'll give you a moment to ask any questions you might have. We've got the QR code back up there, so scan that. We've already had a bunch of questions come through. We will, of course, be back next month for BrisScience. We will announce that speaker very soon, so watch this space. Sign up to our mailing list if you haven't already, and watch that. Also, while we're talking about it, next month we have Nobel Prize winner Donna Strickland coming to present. Sorry, not next week, next week. Next week she's actually presenting here at a UQ lecture right here in this venue, same bat time, same bat channel. So do we have a little QR code for that one too? I believe we do. Oh, look, there we go. So she was, yes, the Nobel laureate in physics in 2018. So she's going to be doing a great presentation next week at 6 o'clock here. So if you're keen to come to that, grab that QR code now, and that'll be another amazing presentation. All right, and of course, don't forget that all of these talks go up, well, the BrisScience talks go up on YouTube, so make sure you hop on there. This one will be up there next week, and you'll be able to watch all your favourite moments again. Okay, we have some questions. Ayan and Nanya have asked a couple of questions around the thermal properties of these crystals. And what is the impact of exposing them to cold or heat? Any thoughts?
So that's very interesting. We've actually done quite a lot of these studies, but they're not fully worked out yet in terms of our understanding of them. What we do to do that is we take one of these crystals and we tie it in a loop and we take it down to the synchrotron and we do exactly the same mapping study that we've done before, but we change the temperature when we do it. And so we've got a temperature range accessible to us of about 100 Kelvin to about 300 Kelvin. So that's essentially from room temperature down to 200 degrees room temperature, down to nearly the point of liquid nitrogen. And what we see actually is that bending wins. So we have two different sets of things that happen. When you change temperature, you get a change in the way the molecules are arranged. Generally, they just expand and contract in a boring sort of way. Generally, it's very linear. Generally, as you cool something down, molecules get closer to one another, and as you expand them, they get further apart. But we see that with the bending, we change that. So we reach a state that is different when it's cold and bent to one that's different when it's hot and bent. Some of the other studies we have run in a similar sort of vein involve phase changes. So when you cool something down, you might change its crystal structure by changing its symmetry. And we see some more interesting things there. For example, when we bend a crystal and we cool it down, it stays intact. But when we heat it back the other way, it breaks. And so we change the properties of that reversible phase change by bending it, because it's no longer the same, or it's no longer reversible in the same way that it was before.
Amazing. Greg asks, how scalable do you think this might be? And Lucy has also asked, do these crystals maintain their bendiness as they grow longer?
Okay, so two different things there. How scalable are they? The biggest crystals that we've grown of these materials are about 10 centimeters long. Now, there's no reason that they couldn't be longer or bigger than that, or think about extruding them. But that's one of the things that, as a synthetic chemist, we tend to work on relatively small scales in an industrial sense. We don't go out and make many kilograms of material, and then, I suppose in one sense, we haven't even tried to grow bigger crystals than that. I don't see why we couldn't. The second question then was, how does it scale in terms of flexibility? This is an interesting property of elastic flexibility itself, and probably why elasticity hasn't really been observed in lots of crystals before. And that's because it's impossible for you to bend a cube. How far you can bend something is proportional to its cross-sectional surface area. And it's a thing called its Young's modulus. So the longer and thinner you make something, the more easy it is to bend it, the more easier it is to observe flexibility. So these will be very, very long, very, very flexible as long as we can grow them in a long and thin way. If, as we grow the crystals, they grow out to be a more cubic shape or a different shape rather than being long and thin, they'll still have the elastic properties. We just won't be able to bend them in the same way.
Amazing. There was actually a question, just following by some, I'll come back to that one when I find it again. Okay, we've got a question here from Akiko, is can I bend these crystals with my hands, or is it dangerous to skin?
So first I'll say the toxicity of these chemicals are not known. That's also not something that we do really in chemistry. We wear absolutely safe materials. We wear gloves and what's called personal protective equipment all the time. Would we expect these to be particularly toxic? No. Why not? Because these compounds and their derivatives are used commonly in sun creams, for example, because of their optical properties and their absorption. But have we tested these? No. Would I advise you to go and pick them up with your hands? No. But the skin is a remarkably resilient thing.
Message received loud and clear. Art has asked, sort of coming back to you mentioned that some of these crystals grown in undergrad laboratories, I think that's, yeah. So Art's asked, has anyone discovered these flexible crystals before, or perhaps it's why has no one, if they're ones that were undergrads make?
Absolutely. So this was a great thing that surprised us as well, right? Because the first one that we really made after our first observation was the commonest one, was the one that anybody who studied chemistry at university has probably made in a lab. So it's probably made on a several kilogram scale every year just in Australia, let alone across the world. And so since it was first discovered in 1901, it's probably been made on a kiloton scale. People have made thousands of tons of this stuff, and nobody has ever worked out why. And I think I know the answer, and I think the answer is because when you go back to that first report in 1901, and all of the lab reports that people use to make this thing, the final purification step that they use is to recrystallize the material from ethanol. And that just means to take it up in a very common thing, ethanol, to dissolve it up until it slowly cool down, to grow crystals of it. And when you do that, the crystals don't grow in a long, thin shape. But if you swap that solvent to chloroform, and you dissolve it, and you let it slowly evaporate, they grow in this long habit, this acicular habit. They're long and thin, and you can observe the elastic flexibility straight away.
Well, great message to all the budding scientists out there that there's lots of science waiting to be discovered, right?
Absolutely.
Amazing. You have a couple more questions before we go? Okay. Okay, we've got James. So I think the questions, there's a bunch of them all around these different questions of applications. I know you touched on that at the very end, but perhaps you could just talk a little bit more about that. Where do you see these, what some things they might be used in or how?
Sure. I think the hard part, or the obvious place for this first, is in electronics. There are some examples now where colleagues of ours have taken some of our materials and they've put them into prototype devices. And what they see then is they see a response when they bend the device that has a different property to what it is they would have otherwise. So that could be an electronic circuit, where when you apply a bit of bending pressure, you change the resistivity of that and you change the way that the circuit operates. Or it could simply be that you want to have a flexible component in your computer or in your telephone, and so you need the right crystal to join somewhere to allow for that communication to occur, but in a way that is flexible. If you look, for example, at the way that we use flexible solar panels now, we ignore the elasticity of the crystals themselves. We take smaller parts of crystals, we chop them up, and we put a bit of flexible polymer in between them. So we're not really using the flexible properties of the crystal itself. We're using something else to engineer that property into our bulk material. So if we want to miniaturize things, really, we need to make them smaller, we need to go to crystals. And we need to do that in a way to improve efficiency, to minimize our impact on the world, and to develop in the way that we're doing it. Where will it probably get used first? In some sort of space exploration. That's honestly where it's going to be, where weight is critical, where people want to make things as small and as efficient as possible before eventually we work out exactly how to do it, and it comes back down to being your mobile phone.
Amazing. Maybe then the follow-up question from, I can't remember who it asked, it was Scott. Scott, how much does it cost to make these?
Ooh, that's a good question. Not very much until you build in our time. So, I mean, a kilogram of acetylacetate, the ligand that we use in copper acetate, in copper acac, probably costs about $100 to buy it from a commercial supplier, which means it probably on an industrial scale costs $10 to make. Copper acetate, the other ingredient here, is about the same price. So we could say, let's make a kilogram of this. Our inputs are going to be $20. In terms then of laboratory time, of manipulation of solvents, let's add another $10 onto that, so we're at $30 or $40, but then it's going to take us probably a day or two to do that. So to make a kilo of material, suddenly you're looking at a lot more cost than you would just to have the materials itself. Could you automate that? Could you invest in making something cheaper that takes us out of it? Yes, AI isn't going to do that for you, but you could probably do it industrially. This is the same way that we now make optic fibers, for example, in a completely automated process. If you have the right application, you can absolutely make these things cheap. If you're going to go and sit down and make 500 of these to prototype them, to test them individually, it's going to be very, very expensive.
Amazing. All right. So one last question, and apologies to Ajax. I'm not going to ask your question of, can I use these crystals to attract a partner? Probably the answer is no, Ajax. I'm sorry. So the last question is, if you were given a blank check, what would you want to do? What experiments would you want to run? Where would you go next?
So the simple thing that we often talk about when we're talking about things like the Australian synchrotron is to make things faster, brighter, and hotter. And to do that, we really mean we need more focused X-ray beams, we need to make them smaller, and we need to make the analysis of things faster. I didn't speak about this at all, but when we first did that first mapping experiment, it took about 9 months of a PhD student's time to process the data. Now, about 10 years later on to that, we've been able to automate a lot of that, and now we can normally process the data in about the time it takes us to collect it. So maybe in an hour or two. We can advance in 10 years just in that amount of automation. But if I wanted to do this on thousands and thousands of crystals, I need faster, I need smaller, I need to be able to do it more efficiently so we get the right information out so we can find out how to design them. Because unless we have the information, there's no way we can even narrow down how we might want to make one of these conduct electricity, for example.
Amazing. Well, things to look forward to for future experiments and hopefully future talks. Can you please join me in thanking Professor Jack Clegg?